I'm going to go through these problems on this circular motion 1. So let's see what we got here. Bowling ball rolls down the hallway. To curve the ball in a smooth circular turn to the right, so turning to the right, draw a picture to indicate how you would push on the ball to make it turn. So this is if I was going to draw like an overhead view, and I want it to turn, and I'll make my little X here, like that's the center of the circle. If I wanted to turn around the circle like this, then if it's rolling this direction, right, if this is the velocity of it, I would have to tap on the ball toward the center of the circle. That seems weird to you if you're like, no, that doesn't make sense. This is the path of it, right? It's going like this, turning around. If that seems wrong to you, then go get a bowling ball and a broom and see what happens. But this is not fake news. That is the real deal right there. So you have to tap toward the center of the circle. If you want, you could go back to the Unit 4 at the beginning and look at those broom ball videos and watch those teachers trying to make that go around there and around that column, and see what you think about their technique. Now I didn't tell them this ahead of time, and they may or may not have had some idea what to do there, but you should check it out. They did not do a great job, if you remember. While you're curving the ball's path, are the forces on the ball balanced? No. We know that if you have circular motion, there must be unbalanced force toward the center of the circle. And not only do we know that, we now know from your notes that that's got to be equal to mv squared over r. That's how much unbalanced force you need excuse me, toward the center of the circle. Draw a force diagram for the ball. So let's see, if we wanted to, how about like the rear view, like from behind, like at ground level behind the ball, like we're kind of chasing behind the ball. Then if that's the ball, there would be the force of gravity straight down, there's support force, or normal force would be straight up, and then this would be like the force of the broom toward the center of the circle, right? That's like if we were chasing the ball and it was turning to the right. So if we were like looking kind of this way at it, that's like a little eye looking that way. That's a weird looking eye, sorry. Is the ball accelerating? Well, if there's unbalanced force, then there must be accelerating. Yes. And if you're thinking to yourself, no, it's not accelerating, it's like going the same speed. That's true, it's maintaining the same speed, but the direction is changing. So velocity is both speed and direction, and those things do not change for free. If they're changing, that's what acceleration is. Acceleration is change in velocity. So acceleration can either change the speed of something, which is what we've been looking at all along here up to this point, or acceleration can change direction, or both. If you think about projectile motion, like from Unit 6, there the downward acceleration of gravity is changing both the speed and the direction of the ball. In this case, the tapping toward the center on this bowling ball, that's changing the direction that the ball is going in, but not the speed if we tap it just right. So if so, what's changing about its velocity? The direction is changing. Not the speed, the direction. An airplane banks and makes a wide circle. Draw a force diagram for a head-on view of the banking plane. Okay, so I'm going to draw that over here. So the plane is like banking this way, and we'll say if it's like flying toward us, then the center of the circle is over here. So what's gravity doing? Gravity's doing the same thing it always does. It's just not caring and doing its downward gravity thing. Now, if the plane is banking like this, the lift force on the wings, that's kind of like a support force. It has to be perpendicular, like pushing straight up on the wings. So if the plane banks, that's going to tilt that lift force like this. And if we break that into components like this, then we can see, okay, so if the plane's like turning like this, going around in a circle, then this and this are balanced, and this right here, that is where the unbalanced force toward the center of the circle is coming from. So this is actually an explanation for why planes, sorry, that's supposed to be force of lift there, why planes bank when they turn. Draw a force diagram for a head-on view of the banking plane. Got it. Name the force that allows the plane to travel in the circle. So that would be, if we knew this angle right here, then this right here would be the adjacent. It would be the cosine component of the lift force. If you just said the lift force, I think that's probably pretty good. It's part of the lift force, right? Here, car enters a circular turn. Name the force, which is an interaction between objects, nice little reminder there, that allows the car to travel in a circle. We talked about this in the notes. It's the friction force. In what direction does this force push on the car toward the center of the circle? Draw a force diagram for the car as it approaches head-on. So coming right at us, if it's turning this way like we had in our notes, there's no motion in the up-down direction, right? That'd be weird. And then there's the force of friction toward the center of the circle. Describe the motion of the car if the force you described in part A suddenly vanished. So if the force of friction disappears all of a sudden, like you hit a patch of black ice or something, then the car would go at a constant velocity. You're like, well, I thought I was already going at a constant velocity. No, the direction's changing here. Constant velocity means same speed and direction. So it doesn't turn anymore. Right? That friction force is allowing for the direction to change. If you have no force toward the center of the circle, whether it's an airplane or a car or whatever, then it will not turn. Just go in a straight line. All right. Hey, we got some numbers here. If the 35-meter radius turn is level, the car has a mass of 1,200 kilograms. This just means that the road's not banked. So that makes things way more complicated, and we're not going to deal with that. And the coefficient of friction is 0.85. What's the maximum speed that a car can travel through the turn? Okay, that might sound kind of hard, but remember that same as the notes and same as our force diagram here, the only thing toward the center of the circle is that force of friction. So that means unbalanced force towards the center is equal to the force of friction. And I know that unbalanced force, when I have circular motion, must be equal to mv squared over r. That's our big new equation. It's the only new equation from this unit, in fact. And the force of friction, I know, is equal to mu times the normal force. And I also know that from my force diagram here, that the normal force is equal to the gravitational force. And maybe I'll just make another copy of that force diagram here. And I'll put in what numbers I can. So if the car has a mass of 1,200 kilograms and the force of gravity is 12,000 newtons, and so is the normal force. So I think I have a whole lot of stuff in this that I can plug in, right? I know the mass of the car. I'm looking to find what that maximum speed is. The radius is 35. The coefficient of friction is 0.85. And the normal force is 12,000. So I think that I can do some algebra and solve for V here, right? Do some off-screen algebra here. So the maximum speed the car can go around this turn is about 17 meters per second. It's about 35 miles an hour. Just check my math there, make sure that that's good. Yes. Looks good. All right. The International Space Station orbits Earth every 90 minutes. Name the force that allows the International Space Station to orbit the Earth. Well, if we drew a picture of this, here's the Earth, there's North America, and South America, and there's some other stuff. Oh, that's good. Look at that. Nice. And then there's like Ireland and England, and Europe, and anyway, I should have quit while I was ahead there with North and South America. And then here's the International Space Station. If you're thinking to yourself, oh, Mr. McGrath, it's not that close to it's actually way closer than that. It's like super close to Earth. It's in low Earth orbit. What is the force on the International Space Station that allows it to stay in orbit? Well, it's the force of gravity, right? Toward the center. Explain why the space station doesn't crash to Earth due to the force on it. Well, just like any other thing moving in a circle, if it's going the right speed, right, when you do the mv squared over r, if it's got the right v and it's got the right r, and that matches its gravitational force, then it's the same reason that when there's a friction force toward the center of the circle that your car is driving in, it's not like your car goes slamming into the center of that circle. It keeps moving around the circle. So why the space station doesn't crash? Because it has the right velocity and radius. So this is the, you can't just hurl something up out of the atmosphere and cross your finger. Well, you can hurl something up into the atmosphere, cross your fingers, and hope that it goes into orbit. But it's not going to go into a circular orbit unless you get it just to the right altitude and just going the right speed. Then you can get it into circular orbit. So it's a tricky game. We humans have got pretty good at it. There's lots of satellites in orbit around the Earth, including the International Space Station. Okay, draw a force diagram, side view for a roller coaster on a level track. So I'm going to make, on a level track. So here, there's the track. There's the force of gravity. There's the normal force. There's probably some friction, but if it's just going along, if we're assuming that there's no friction, then it would just be going along at a constant velocity here, because those would be balanced. Let's see if I answered the question. Okay, should the forces perpendicular to the track be balanced? Yes. Yes. If the forces are unbalanced, explain why there is a net force in the direction of the net force. So they are balanced, so we don't have to do that, right, because they are balanced. Draw a force diagram of the roller coaster traveling over the top of a hill. So these should remind you of the diagrams from your notes. Where's the center of the circle? It's down here. So that means that is the winning direction, which means that the normal force has to back off. Of course, gravity is not going to change because gravity doesn't care. But the normal force can back off. For roller coaster, should the forces perpendicular to the track be balanced? No. If the forces are unbalanced, explain why there is a net force in the direction of the net force. So there must be net or unbalanced force. That means the same thing, net force, unbalanced force. There must be unbalanced force toward the center of the circle. Now the roller coaster goes through a valley. We know, well, we just said it, didn't we? Must be unbalanced force toward the center of the circle. Center of the circle now is up here. So the support force is going to have to win versus gravity. If the forces are unbalanced, so let me back up. Should the forces on the track be balanced? No. If the forces are unbalanced, explain why in the direction. Well, same thing. There must be unbalanced force toward the center of the circle. So it's the same answer whether the center of the circle is up here or down here, right? There's got to be unbalanced force toward the center of the circle. And gravity just doesn't care about me, you, or the roller coaster, or the International Space Station, or anything else. Just keeps pulling everything down. All right, there you go.